Good morning, everybody. So today, the idea was to finish the lecture on model predictive control, which we started last week. I expect this should take less than 2 hours, so probably we'll have some spare time to start digging into some applications of optimal control. So before we move on with MPC, let me briefly summarize what we had covered last week. So we introduced the key concept of MPC, which is this idea of solving an optimal control problem inside a control loop, and then only using the very first optimal control input computed. And at the next time step, we basically throw everything away and we repeat the process by using as initial state of the optimal control problem, the measured state of the system right now, or an estimate in case we don't have direct sensor measurements of the whole state, which is most often the case in robotics. We typically measure positions, we don't measure velocity, so we need to estimate them. So this is a very simple idea, and once you know how to solve an optimal control problem, well, you already know how to do MPC, because there is not much to add on top of that. However, we have this issue when we do MPC, that's the trajectory that we predict at a given time. Since we only apply the first control input and then we re-optimize, well, it's not going to be the trajectory that we end up really executing. So the prediction is not going to match with the actual state trajectory, and that could lead to trouble such as feasibility issues, stability issues, and then we have a third challenge of MPC, which is computation time, because we need to solve this optimal control problem very fast in order to be effective for real-time control. Last time we covered everything I had to tell you about feasibility. We started from this idea that if we were able to solve infinite horizon optimal control problems, then actually feasibility and stability wouldn't be an issue, because having an infinite horizon guarantees that the problem is going to be always feasible and always stable. So unfortunately, infinite horizon is not something we can really achieve in practice because it's unfeasible. And the idea that we can work with is instead to add a terminal cost and a terminal constraint that mimic what we would have with an infinite horizon problem. The idea is that this terminal cost should represent the cost that we pay starting at that state and going on for infinite time. And this constraint set instead should encode basically all the constraints from there until infinite time. So if we satisfy the constraint at time step n, that should imply that we are able to satisfy the constraints in the future indefinitely from that point in time onward. That's a very ambitious goal, to be able to compute such terminal cost and such terminal constraints, but luckily we don't really need to achieve that high standard. We can show that this works even with a easier terminal constraint and terminal cost. In particular, for the terminal constraint, we saw that we just need the terminal constraint set to be a control invariant set, because if the terminal constraint set is control invariant, then we have this theorem that says that the MPC is always going to be feasible, assuming it's feasible at the very first iteration. That's a requirement. A control invariant set is a set such that once you are inside the set, you can remain inside the set forever. It's a very simple definition. Unfortunately, computing control invariant sets in general for nonlinear systems subject to nonlinear constraints is a very challenging problem. There are some trivial ones, such as the set of zero velocity states for a robot manipulator. That's typically a control invariant set, but it's a very small one. And that comes with some downsides, which is that the robot is not going to be able to move fast. Or to be more precise, how fast the robot can move depends on how long the horizon is. So if you want the robot to move fast, to be high performance, then you need a long horizon, but then you need to pay for the long horizon in terms of computation time. So it's always going to be a trade-off between computation time and performance of the system. If instead you want to work with a bigger control invariant set, which is not this trivial one, I showed you that there is a technique that we can use, which tries to approximate an n-step backward reachable set, which is a special kind of control invariant set. And this technique works by sampling random states in the state space of the system. For each sampled state, we try to solve this optimal control problem, which basically tries to reach an equilibrium state starting from the sampled state while satisfying all the constraints of the robots. And if that problem admits a solution, so if we can find a solution, that we know that this sample state belongs to this backward reachable set, otherwise it doesn't. And so by sampling many states and solving these optimal control problems, we are able to basically create a data set. And this data set is going to contain pairs of state and label, where the label represents whether the state belongs to the set or not. And then we can generalize this data set by using a neural network, which we train to classify states into these two classes, so belonging to the set or not. And then we can use this neural network as a terminal constraint in our model predictive control problem. So that's kind of an advanced method to ensure recursive feasibility in MPC. It's approximate, so we don't have any strict guarantees, but that's kind of the best we can do with nonlinear systems. And that's where we stopped. So we have to cover now the stability issue and the computation time. Any question on what we covered last time before we move on? Seems not. So next issue is stability. To talk about stability, we need to introduce the concept of Lyapunov functions. Have you already encountered Lyapunov functions before? Raise your hand. Okay, a few of you, but not many. So Lyapunov's theory is this theory that is used for proving stability of nonlinear systems. It's a very well-known tool in nonlinear control theory. Here we're going to introduce only the concept of exponential Lyapunov functions. And these are functions that map the state of the robot into a scalar value. And such a function is indeed an exponential Lyapunov function if it satisfies these two conditions. The first condition is very easy. It's basically saying that this function must be both lower bounded and upper bounded by a scalar function of the norm of the state. And this has some implications. Well, it implies that the function is always non-negative, because if it's lower bounded by something that is always non-negative, well, of course, it's always non-negative. And it's going to be 0 for at the origin. So v of 0 is going to be equal to 0. And whenever x is not 0, then this function is going to be positive, strictly positive. But this one is the easy condition to satisfy because it's pretty trivial to figure out a function that satisfies this condition. The tricky condition is the second one. So this condition says that basically this function decreases along the trajectories of the system. So if you keep evaluating the function along the trajectory for every successive state, this function decreases, and it decreases by a quantity which is at least linear in the norm of the state. So the decrease has at least a certain rate. So what this inequality is saying is that this Lyapunov function, if you evaluate it at a state x, and then you evaluate it at the state after that, which is f of x. So f is the dynamics of the system. Here I'm neglecting the existence of control inputs u. I'm just representing it as f of x, assuming the system is autonomous, or what there is a fixed controller, so even u is a function of x. This function is decreasing. I mean, you can rewrite this. Maybe it's easier for your understanding to rewrite this as v of x1 is smaller than v of x0 minus alpha 3 norm of x0. So maybe it's easier to understand if I write it down in this way. So this Lyapunov function, every time you move forward of one time step, decreases because it's smaller than the value it had before. And it's smaller by at least a quantity that is proportional to the norm of the state. So not only it decreases, but it decreases with a certain rate. So this alpha 3, alpha 2, alpha 1, they are arbitrary positive scalar values. They just must exist. It doesn't say which values they should have. Whatever value is fine, as long as it's positive. So if you find an exponential Lyapunov function, so a function v that satisfies these two conditions for your system, then this implies that the origin of your system, so x equals 0, is exponentially stable. What does it mean that the origin is exponentially stable? It basically means this, that from any state that you start, the starting state is x0, then the norm of the state is decreasing exponentially. So the state is converging to the origin with an exponential rate. I'm not going to show you the proof, but I think that even intuitively it makes quite sense that once you have these two conditions, you can prove this one. Because if v decreases with a given rate and v is lower and upper bounded by the norm of x, then also the norm of x is going to decrease with an exponential rate. So this is going to be the theory that we are going to exploit to prove the stability of our MPC controller. So this is just the starting point. So instead of showing that the state is is exponentially, the origin is exponentially stable, we can just focus on finding an exponential Lyapunov function for the system, and then we have this theory that translates that into a proof of stability for the origin. So now the question is, okay, if we have an exponential Lyapunov function, we can show the system is stable, but how do we find an exponential Lyapunov function? And in MPC, typically the idea is to use the cost function as a Lyapunov function. So that's the idea that we're going to work with. When you solve an optimal control problem, you have your cost function, which is the running cost plus the terminal cost. And what we are going to do is that we are going to figure out conditions on the terminal cost such that the overall cost function is an exponential Lyapunov function. In particular, the terminology I'm going to use is the value function, which we haven't really discussed yet. But the value function is nothing more than the optimal value of your cost function. Okay. So when I'm going to say value function in the following, you should just think the optimal value of the cost. So that's exactly the idea that I'm exploring here, using the value function, which is the optimal cost, as a Lyapunov function to prove stability of the origin. So here in this diagram, I'm representing the time axis. So here we have time 0, time 1, and we move forward until time n and time n plus 1. So the value function at time 0, it's a function of the state at time 0, and it's just the summation of the running cost for time going from 0 to n minus 1 plus the terminal cost evaluated at the terminal state. That's my value function. So I depict all the terms of the value function of x0 in blue here in this on top of this axis. So we have the running cost at time 0, which depends on x0 u0, running cost at time 1, which depends on x1 u1, and so on until n minus 1. And then the final cost, which is the terminal cost, is only a function of the final state xn. Okay. So here is my definition of the value function. And the question I need to answer is this value function a Lyapunov function? Under which conditions that happens? Well, we can go back to the previous slides and see that the main requirement for a function to be a Lyapunov function is this one, that it decreases along trajectories. So we just need to check under which conditions this is satisfied for the value function. So
what do you mean by d1 star and
I'm getting there in a moment. So I need to check whether this value function decreases along trajectory. So I need to compare the value at time 1. That 1 shouldn't be there. The value evaluated at x1 with the value evaluated at x0. However, it's hard to do this comparison. It's much easier to compare the value function at time, at state x0 with this suboptimal value at state x1, which is basically the value that I would have if I were to use basically the same trajectory computed at time 0, even at time 1. So what I'm saying, connecting this to this plot here, is that when I typically move from time 0 to time 1, I re-optimize the trajectory, and the trajectory that I get is completely different from the one I had before. So it's hard to compare the cost of these two trajectories. But what I can do for making this comparison is that I can work with a suboptimal trajectory at time 1, which is the same trajectory that I had before, plus an extra step, which can be whatever. And I know that the cost of this is going to be for sure worse than the optimal cost, which could be of a completely different trajectory.
Well, that doesn't like make it's just an assumption that our Lyapunov function is good enough, and because if it's suboptimal, there's a higher chance of the Lyapunov. Oh no, wait, it needs to decrease. So if it's decreasing for the suboptimal,
if it decreases for the suboptimal, it's also going to decrease for the optimal one. So basically, I'm working with a sufficient but not necessary condition. So I'm being conservative by using this suboptimal value function basically to check the decrease. Yeah.
Could you repeat this message?
Yeah, I'm going to repeat it at least 3 times because it's complicated. So let me work out the math, and then we repeat it over and over again. So instead of working with the optimal value for state x1, I'm going to work with this suboptimal value. That's why I removed the star. So this suboptimal value is for sure not better. So it's for sure greater than or equal to the optimal one by definition of suboptimal. And this is the cost that I pay following the same trajectory that I had optimized at time 0. So I sum the costs from time 1 to time n, and then I have my terminal cost corresponding to the state xn plus 1. And I represented in green the terms of Vx1 here on top of the time axis.
How do I calculate the n plus 1 step?
The xn plus 1 can be whatever. At this point, it's going to be clear later what are the properties that we need for making sure that we have this decrease, and those are related to what happens at xn plus 1. So the reason why I need to do this, so assuming that the two trajectories are the same, is that when I compute the decrease of this value function using the suboptimal one, I'm basically computing the difference between all the green terms and all the blue terms. And you can see that all the ones in the middle of the trajectory are going to be the same. And so when I compute this difference, they all simplify to 0. If instead the two trajectories are completely different, I don't have any of that happening. And so the math becomes much more difficult to work with. Okay. So if I do this difference, the only terms that are not canceling out are 4, which are this, 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 and this. Those are the only terms that are different from the top row and the bottom row. And so the expression I get is the following one. And from the previous slide, you remember that the condition is that my Lyapunov function should decrease by at least something that is proportional to the norm of the state. And that's how I get the right-hand side of this inequality. So, okay, I'll let you finish writing. So if this is satisfied for v of x1, which is a suboptimal value function, then this is also going to be satisfied for v star of x1, which is the optimal value function, because the optimal value function is smaller. So by decreasing this, I'm also I keep satisfying this inequality, because if it's a smaller than inequality. So basically, I'm transforming my initial question of is my MPC stabilizing the system? I first transformed it into, can I find an exponential Lyapunov function for this system? And now I've transformed it again into, can I ensure that this inequality is satisfied? And this inequality, I can interpret it as an expression that depends on the terminal cost, because that's my ingredients I can work with. That's the only part of the problem that allows me to manipulate the controller, because everything else I cannot really change it. The running cost is assumed to be like task specific, so it's not something that I can work with. I can change just to stabilize the system. Whereas instead the terminal cost is something that I added, if you remember, to kind of compensate for the lack of an infinite horizon. So the question here is, can I figure out a terminal cost for my MPC controller such that this inequality is satisfied? And if so, I have a guarantee that my MPC controller is stabilizing the origin of the system. And as I was saying, this condition is sufficient, but not necessary, because I'm using this suboptimal value in this for computing this condition. And so I'm actually being conservative. So it's possible that you cannot figure out a way to satisfy this, but still your controller is stable. You're just not able to prove it. Any question?
Probably the Lyapunov function space. Like if I have this and I found that my Lyapunov function exists, then I know my controller state function will look just like it. So
Yeah. We still need to figure out how we do that.
Yeah, okay.
So we are not done yet. We are in the middle of the process. So now let's take a look at this inequality here. This term is the easy one because typically when you do stability analysis, that's something actually that we had to do even in the case of the infinite horizon. You always assume that your running cost is lower bounded by the norm of the state. So that's something that we also covered here. You remember we had to take this assumption. The running cost is greater than or equal to some linear function of the norm of the state. So most stability analysis of, in general, well, of MPC starts with that assumption. So that's also an assumption we are going to take even in this case. So the last term there, if this is greater than some norm of the state, we have a minus in front, we can be sure that this is always going to be negative. And so if this part was 0, then we would be good. Because this one is for sure negative and it satisfies the inequality. So we just basically need to worry about these first 3 terms. It doesn't need to be exactly 0. We just need it to be smaller than or equal to 0. Because if it's smaller, well, it just helps satisfying the inequality. So that's the condition, the main condition we need to work with. So the summation of these 3 terms being smaller than 0. Now I'm going to give you the whole list of assumptions that we need to satisfy. But the main one is going to be this one. So this summation being smaller than 0. So this is a whole list of assumptions that we really need for ensuring stability. We need to have the origin of the system, which is an equilibrium. That's a really reasonable assumption. If you want to show that the origin is exponentially stable, well, it needs to be an equilibrium. Your cost function should be 0 at the origin. Again, quite reasonable. Your terminal cost should be 0 at the origin. Reasonable. If the origin is the point that you want to reach, why should you pay a cost once you reached it? So those are easy ones. The tricky one is the second assumption, which is the one we just described. I'm just basically it's saying that these 3 terms here should be smaller than or equal to 0. I've simply moved this one to the right, and I get this expression. And this is really a condition on my terminal cost. And if I look a moment at it, what it says that if I compute my terminal cost along over the trajectory of the system, it should decrease by at least a quantity that is my running cost. And then there is a third assumption, which is what I was telling you before, is that your running cost should be lower bounded by some linear function of the norm of the state. So if these three assumptions hold, then we have that the value function is an exponential Lyapunov function, and so we have that the origin of the system is exponentially stable. So the MPC is stabilizing the system. So where does this lead us? We are now actually in a very similar situation to where we were before with the feasibility issue. Before we had introduced this concept of control invariant sets. So we have transformed the problem of ensuring feasibility into the problem of finding a control invariant set. And then we discussed how, in general, it's very difficult to find a control invariant set. Here, it's very similar. We have transformed the problem of ensuring stability into the problem of finding a terminal cost that satisfies this condition. And then what I'm going to tell you is that, in general, it's very difficult to find a terminal cost that satisfies this condition. But there are some special cases that allows us to satisfy this condition. And there are some sampling-based methods that use function approximation techniques that are able to approximate terminal cost that should satisfy this condition in an approximated sense. So yeah, okay, so here is just a recap of what we have been discussing. Assumption number 2 ensures that this first part is smaller than or equal to 0. Assumption number 3 ensures that this second part is smaller than minus some linear function of the norm of the state. And so if you take the sum of these two, you know that the inequality is satisfied.
Why is it alpha 1 and alpha 3 shouldn't be both?
Yeah, I mean, in practice, they are the same. It's just that here I used alpha 1. So when I reported it below, I also used alpha 1. But they are arbitrary positive scalar values, so they can be equal. A small note, maybe it's trivial, but I want to clarify. Here we have been working all the stability derivation on the assumption that the state that we want to stabilize is the origin. So the state x equal to 0. Of course, in practice, on a real system, the states that you may want to stabilize may be different from the origin. Maybe you want to stabilize your robot in a configuration which is not with all the joint angles equal to 0. That doesn't change anything with respect to the theory, because you just need to define a new definition of the state where you add a shift so that the state that you want to stabilize corresponds to 0 in this new shifted state space. Okay. It's kind of trivial, but here I basically wrote down the math of how you do it. You're just shifting everything. Similarly, the fact that the origin should be an equilibrium for the control equal to 0. It doesn't really have to be the control equal to 0. For instance, if you want to stabilize your robot in this configuration, well, the control inputs for stabilizing this configuration is not 0 because you need to compensate for gravity. But you can easily achieve that by introducing, again, a new definition of your control input, which has a shift with respect to the standard definition, so that the gravity compensation for this configuration corresponds to the new control input being equal to 0. Okay, you're just shifting stuff. So what options do we have to stabilize, to show the stability of our MPC controller? So in general, the ideal thing would be to pick the terminal constraint and the terminal cost using some sampling-based approach and function approximation techniques such as neural networks that ensure that the terminal constraint set is control invariant and the terminal cost satisfies this inequality here, so that it can decrease by at least the running cost for every possible state that belongs to our terminal set. So that's the more general framework that we have presented. I'm not explaining you how the sampling-based methods for computing the terminal cost works, but they are quite similar to the ones that I've explained you for the terminal constraint. If you don't want to go through the painful process of computing such complex terminal cost and terminal constraints, you have other two options. A very easy one is to choose your terminal constraint set to be just the origin, so just the states that you want to stabilize. Of course, that's a very small terminal constraint. It's quite similar to the idea that we have explored of choosing the terminal constraint to be the zero velocity set for the manipulator. So you pay in terms of having a small basin of attraction, because you can never basically go very far from that from the origin if that's your terminal constraint set, because you need to be able to reach the origin within your typically short time horizon. So it's a controller that, yeah, it's recursively feasible and stable, but it only allows you to stay very close to that terminal state. And you can easily show that if you choose this terminal constraint set, then this is always satisfied automatically because you need to satisfy this only for the states that belong to your terminal constraint set. And if your terminal constraint set is just one state, well, then you need to satisfy this only for that one state. And it's trivial to check that for that one state that is satisfied, because actually this becomes zero, this becomes zero, and this becomes zero. So they're all zero and the inequality is satisfied. So this leads to, let's say, poor performance, but very strong guarantees. And it's very easy to implement. Otherwise, third option, pick an horizon that is large enough and don't use any terminal cost, and just use your standard constraint set as terminal constraint set. And this in practice works quite well. Yes?
It's like terminal cost and defend and just pray that this stays.
Yeah, I mean, you don't need to pray. You just run it. But yeah, that's kind of the idea. I mean, the point I want to make here is that by increasing the horizon, all the problems of stability and feasibility, they disappear. So if your problem is sufficiently simple and your implementation is sufficiently performant and you have a good hardware on which to run your solver, then you can choose a quite long horizon and basically forget about all the feasibility and stability issues. They become much more important when you have a short horizon, which is the case when you have a complex system. So depending on the system you're trying to control, well, you might decide to pick 3 rather than 2 rather than 1. They come with different pros and cons. Like if you're controlling a differential drive robot, so like a unicycle, like a Roomba robot with 2 wheels. So that kind of robot has a 3-dimensional state space because you only model position in 2D and or one angle for the orientation. So you have a super small state space, super simple dynamics. You can work with a quite long horizon, and then everything automatically works. If you're on the other side of the spectrum, if you're controlling a humanoid robot with a state space of 100 dimensions, very complex nonlinear dynamics, then you will need to work with a very short horizon for your MPC. And at that point, all these issues of stability and feasibility, they become real. And so you need to worry about this. So depending on the applications, you can decide which options you want to choose. What makes it tricky is that we don't know exactly how large n should be to make option 3 a good option. So you need to figure it out by trial and error. So you just test it in simulation and you see, does it work? Do you end up with an unfeasible problem? Do you end up with an unstable behavior of the robot? If not, then you're good to go. What we have seen so far is stability for a state, a single state. So what we showed is that the origin of the system is stable, it's exponentially stable. However, very often we don't want the robot to just be stable at one point, because that would correspond to basically the robot staying there. Okay, reacting to perturbations, if you push it, then it goes back, but that's not a very interesting behavior. We typically want the robot to move. And maybe the most common case is to do trajectory tracking. And here I just wanted to reassure you that there are extensions of all the stability theory we have been discussing to deal with trajectory tracking. The way you do it is typically to introduce a new definition of the state, which is the difference between the state of the system and the desired state of the system defined by the reference trajectory, so that now your system becomes a time-varying system, even if the real dynamics of the robot is not time-varying, it doesn't depend on time. And then we have extensions of stability for time-varying systems that we can use for proving the stability of the robot with respect to a trajectory. And also the assumption that we took that your running cost should be lower bounded by some norm of the state. There are theories of stability for MPCs that do not take that assumption, and those are under the name of economic MPC in the literature. I never understood why they chose this name, but that's the name you have to look for. But these are much more convoluted and advanced, so we're not covering them here. It's just for your reference in case you're interested. So we have to tackle now the very last challenge of MPC, which is a much more practical one, and that's computation time. And on this, I don't have much to tell you. Everything is in this slide. And here we just have a couple of ideas, very simple ones, but that make a big difference in practice. The key idea for reducing computation time of MPC is to exploit initial guesses, so warm start. And what you do is that instead of solving the problem from scratch at every control loop, you reuse the solutions that you computed at the previous control loop as an initial guess for finding the new solution. Because it's true that the new solution is going to be different from the previously computed one, but it's not going to be extremely different in general. Most of the time, it's going to be quite similar to the previous one. And so if you use the previous solution as an initial guess, as a starting point for the optimization process, your solver is going to converge much, much faster. So the only thing you have to do is to shift the trajectory by one time step backward, because now one time step has passed. And so what was time 1 before is time 0 now. What was time 2 becomes time 1. And so you need to shift the trajectory backward, which means that you don't have an initial guess for the very last time step, because that was not in the preview window before. And for the very last time step, you need to figure something out. Maybe you just set it to 0. It's a reasonable option. Or maybe for a robot manipulator, you can set it to the gravity compensation torques. That's also a reasonable option rather than 0. And there you have a reasonable initial guess, which makes the solver converge much, much faster. Another idea that is often used in practice is that instead of letting the solver iterate until reaching the convergence threshold that you've set, which, by the way, you should set quite large when you do MPC. You don't use convergence threshold of 10 to the minus 8. Rather, you use 10 to the minus 4. So it converges faster. But you can be even more aggressive than that. So you just don't let the solver iterate until convergence. You just let the solver do one iteration or 2 iterations, depending on how much computation time you have. And then you take whatever trajectory the solver computed in those 2 iterations. It's not going to be optimal, of course, but it may be good enough. And what has been shown actually in many papers is that it's better to work with a suboptimal trajectory obtained fast than to work with a more optimal trajectory, but with a larger delay. So very often, people who do MPC in practice, they just do one iteration. One thing that happens is that since you only do one iteration, your trajectory at the end of the horizon is of very bad quality, because at the end of the horizon, you just started with an initial guess, which is in general quite poor, like 0 control input. And so by doing just one iteration of optimization is not improved a lot, and it remains a quite poor guess. But what happens is that you're not really using the end of the horizon. You're only using the very beginning of the horizon. So you don't care if the end is bad. And that end of the horizon piece of trajectory, once it gets to the beginning of your MPC horizon, it has gone through n steps of optimizations, because every time you optimize it while it moves backward. And so once it gets to time step 0, it's quite good. So even if you do just one step of optimization, since you're initializing with the previous solution, the control input that you have at time 0 of your horizon has gone through n steps of optimization, which makes it quite good. And so this works. Another thing that you can do is to use hardware accelerators. It's not super common, but there are some people who are now using GPUs for solving the trajectory optimization problem. And so maybe they can solve it like 3 times or 5 times faster than on a CPU. And well, of course, goes without saying, you need to implement this in a very efficient way. You cannot just implement your solver in Python and hope it works. When you do MPC, you need to have a solver which is implemented in a compiled language like C++. And there are solvers that are implemented exactly for doing MPC. So they try really to optimize every little bit of computation so that they can give you an answer as fast as possible. Like Kazadi, the solver, well, Kazadi is not a solver, IPOpt is the solver that we are using behind Kazadi for solving optimal control problems, is not meant to be used for MPC. So that's fine for doing offline trajectory optimization. But if you want to do MPC, there are other solvers that you can use that are faster than IPOpt. IPOpt is meant to be very robust. So it's meant to work with any problems that you throw at it, but it takes its time to find a solution. It's not meant for finding a rough solution fast. It's meant for finding a good solution slowly. There are other solvers that are more suitable instead for doing MPC. So if you want to do it, you have to switch to one of these other solvers. And that was the last slide I had on MPC. Do you have any question before we take a break? Good. Then I'll see you back here at 40.